again, these two usually are used to go from polar, given r and theta, to rectangular, finding x and y. All right. So we did some where we were converting points, and then we started doing a couple with converting equations. So let's see if we can finish off the converting equations today, assuming this thing wants to work at some point today. Why are you not loading? Hey, there it is, finally. All right, so in this case, we're given an equation that's in rectangular form, and it wants us to convert to polar form. So again, we want to use our conversions that pardon me, that change our polar into rectangular, which I just mentioned a little bit ago, or those second step, right? So what should we plug in for x to convert it over to polar? What should go in for x? What does x equal in terms of r and theta? R cosine, good. So we can do this as 4 r cosine theta. What should we plug in for y? Yeah, r sine theta, good. So this is, again, we're changing it from a rectangular equation to a polar equation. A lot of times the problems will ask you to solve for r. What should I need to do to the left-hand side if I want to try to solve for r? Say again? Well, if I just want to get r by itself, what do I notice is in both of those terms? I want to get r equals something. I want to try to isolate the r. What do I notice is in both of the terms on the left-hand side currently? There's an r, so what can I do with it? Factor it out, good. And then to solve for r, I just need to divide. So we'll get r equals 18 over 4 cosine theta minus 3 sine theta. So I know it's been a little bit, but remember when we started talking about polar, we said polar coordinates are good for describing regions or graphs that are circles or pieces of circles, but not necessarily so great for describing other types of shapes. Well, if I start with that equation, that 4x minus 3y equals 18, and think about its graph, what is the graph of 4x minus 3y equals 18? What's that the graph of? Or what is the graph of that equation, I guess I should say. If you were to graph it, what kind of big shape would you get? This is an algebra 1 question, right? What kind of graph would you get? It's a line, yeah. This is a graph of a line, right? Are lines circles or pieces of circles? Not a trick question. Are lines circles or pieces of circles? No. Okay? So notice that this equation for r in terms of theta isn't particularly nice. I mean, it works, we get one, but it's not particularly nice. Because again, polar, remember how we graph in polar, right? You go out from the pole, out from the origin, and rotate, which is why it does a good job of describing circle things, not so good at things that are straight. All right, let's look at the next one, where we've got x equals y squared over 5. Again, we can just plug in what x and y are in terms of r and theta. So we can put in r cosine theta in for x and r sine theta in for y. And again, if we can, we like to solve this for r. So if we square the r and square the sine theta, we get r squared sine squared theta over 5. Pardon me. Let's multiply by 5, divide by sine squared, divide over an r. We get r equals, I get a cosine theta, 5 cosine theta over sine squared theta. And just to try to make this look a little bit nicer and also review a couple of simple identity ideas. Sine squared is certainly sine times sine, so I could be a little bit fancy and rewrite this as 5 times a 1 over a sine and a cosine over a sine. Oops. 1 over sine is the same thing as cosecant, and cosine over sine is the same thing as cotangent. Good. Oops. Again, we have a formula here for this particular thing in terms of theta, r's and thetas. But again, not a nice simple formula. Not bad, but it's not nice and simple. And again, because we're thinking about polar being really nice to describe things that are circles or pieces of circles, what kind of a shape is this when you've got an x to the first power but a y to the second power? What kind of a shape do you end up with? Usually you think about it as y equals x squared versus x equals y squared, but what kind of a shape do you end up with? It's a parabola, yeah. This one happens to open to the right, since it's y squared rather than x squared. But this one opens to the right, we get a parabola, and this would give you the same parabola in this case. So again, this is just converting from rectangular to polar. And notice it's pretty straightforward, right? All we did was just take out the x, put in r cosine theta, take out the y, put in r sine theta, and solve for r if we can, right? Agreed? Let's go the other way. There's some of them will involve a little bit more tricky types of things. Let's look at part A here. In part A, we've got r equals 4. Let's just remind ourselves, what kind of a shape do you get if you think about graphing this in polar? This says r has to be 4. What kind of a shape do you get if you graph the equation r equals 4 in polar? Theta can be anything, but r has to be 4. What kind of a shape do you get? A circle, right? It's centered in the pole, radius 4, right? That's why we use r as for radius, right? So we get a circle of radius 4. That's a pretty easy equation, right? This is a constant. In polar, this is a constant function. R equals a constant. That's a constant function, okay? So this is a nice description of a circle of radius 4 centered at the origin, okay? Let's think about how we would convert this to rectangular. Well, using it in rectangular, I want to use one of these two equations if I can, right? Well, does that r equal 4 have any thetas in it? Not a trick question. Does that r equal 4 have any thetas in it? No. Okay. So I probably don't want to use the second equation. What do I need to do to the r equals 4 to be able to use the first equation to convert? Yeah, let's square both sides, right? If I square both sides, we'll get r squared equals 16. Now that I have r squared, what can we replace r squared with? X squared plus y squared. And now we've converted this from polar to rectangular. So notice that if I'm trying to get rid of an r in polar and convert it to rectangular, I probably need an r squared. Okay? To be able to use that x squared plus y squared equals r squared. One way to do that is to square both sides if I see an r in there. Unfortunately, you don't always want to square both sides, and we'll see an example of that here in a minute. Let's look at part B. Part B has theta equals pi over 6. Also a pretty easy equation, right? This one says your theta always has to be pi over 6, but your r can be anything. What kind of a graph would you get if your theta always has to be pi over 6? So the angle that you make with the positive x-axis or with the polar axis always has to be pi over 6, but the distance from the origin, the r value, can be anything. What kind of a shape are you going to end up with? So again, if we have polar axis, the angle we make with the polar axis always has to be pi over 6, but r can be whatever you want. What kind of a shape are you going to end up with? So it won't quite be a triangle because it doesn't chop off, but it is going to be a line, right? So going this way, those are positive r values, and then remember, if it's negative r values, we would go this way, but this angle would have to be pi over 6 all the time. So we get a line going through the pole. That okay? Right. So if I want to convert this to rectangular again, do I see any r's in this equation? Yeah, not a trick question. Do I see any r's? No. Okay. So I probably don't want to try to use the first equation. I want to use the second one. In order to be able to use the second equation, what do you think we want to do to both sides now? Yeah, good. Take the tangent of both sides. Exactly. So do the tangent of both sides. So you get tangent of theta equals tangent of pi over 6. What can we stick in for tangent of theta now? Using our conversion formulas here, what can we put in? Y over x, good. And what is tangent of pi over 6? One over 3, good. And then if I want to solve this for y in terms of x, I can multiply both sides by x. And do I see an equation of a line now? Yeah, we have an equation of a line, don't we? That goes through the origin. Let's look at this next one, where we've got r equals 6 over 5 sine theta plus 2 cosine theta. Now, again, we said that if we have r involved, we might think about trying to get r squared involved so we can use that first formula. But if I try to square both sides in this case, I'm going to get a mess, all right? Especially in the denominator. It's not going to be very helpful. I don't have any conversion formulas that say anything about a sine squared or a cosine squared, right? It's going to be really, really nasty if I try to square this and then try to figure out how to, pardon me, how to convert that over to rectangular. So what might make more sense for this particular problem is just to clear the fraction. Multiply both sides by the denominator. And then distribute your r through. So you end up with 5r sine theta plus 2r cosine theta equals 6. Now do you see something you can plug in to get rid of the r's and thetas? Do you see any substitutions we can make using our conversion formulas? Say again? You have the x and y, right? What's r sine theta equal to? If that one's y, and the r cosine theta is x. Good. So we end up with 5y plus 2x equals 6. And in this case, again, we see an equation of a line. I know it's tempting when you're trying to get rid of the r that you really want to see an r squared, but that usually is a very good intuition to have, to try to get an r squared. However, don't always try to get an r squared by squaring. In this case, we didn't even need an r squared. So make sure you're keeping track of your other conversion formulas as well. Let's look at this last one here, where we've got r equals negative 4 cosine theta plus 2 sine theta. Notice I can't do the same thing that we just did in the previous example because I don't have a denominator to try to clear. However, the previous example does give us a little bit of an insight of what we might want to do. Notice in the previous example, we were able to replace r sine theta with y and r cosine theta with x, right? And I don't have quite that in this case, right? We just have a cosine and just have a sine. However, how could I get an r sine theta and r cosine theta? Just by doing something to both sides of the equation. Multiply by r, good. If I multiply the right-hand side by, if I multiply both sides by r, not only do you get r cosine theta and r sine theta here, what do you get on the left-hand side? R squared, which is also good, right? So first, let's multiply both sides by r. And distribute the r through. So we end up with r squared equals negative 4r cosine theta plus 2r sine theta. What can we plug in for r squared? X squared plus y squared, good. And then what goes in for r cosine theta? X. And what goes in for r sine theta? Y, good. So we get x squared plus y squared equals negative 4x plus 2y. And notice again here, usually you think about just having x squared plus y squared equals a number. You recognize that as a circle pretty quickly. This also is an equation of a circle. It's just shifted where the center is not at the origin anymore. The center of the circle would be at negative 2, 1, as a matter of fact. You can get that by completing the square. But this shows me that I have an equation of a circle. Again, thinking about what you learned in algebra class, circles, not functions of x or y, right? So they don't pass a vertical line test in particular, right? However, we've written this as r equals function of theta. So a circle is a function in polar. It's a function of theta in polar, where it was not a function in rectangular. And again, if you're doing some types of analysis on these types of things, it might be better to have something that is an equation, is a function rather than not. It's chilly enough in here, I was thinking maybe the window was still open, especially since I could hear that blubber. That okay? All right. Notice again, though, like I mentioned before, getting an r squared is a good idea when you're trying to convert from polar to rectangular, but don't just blindly square both sides. Okay. So let's see if we look at the next example. Same thought. Where we have r equals r equals 4 sine theta. What might you think you might want to do to both sides here so that you can convert this over to rectangular? What do you think you might want to do? Yeah, do the same thing we did in the previous one, right? Multiply both sides by r and see what happens. Notice that multiplying both sides by r here works better than trying to square. Because if we try to square both sides, we would get a sine squared, which causes us issues for being able to convert. Right? Causes a little bit of problems. Now what can we plug in for r squared?
X squared plus y squared.
X squared plus y squared. And then what goes in for r sine theta?
4y.
Good, 4y. Good. So we get x squared plus y squared equals 4y in this case. Is that okay? Let's do the next one. The last two are kind of fancy. I'll post the answers to those on Moodle rather than going through them in class. I want to get into some new stuff today. This next one is a little bit fancy, but it's not too bad. If we have r equals 3 secant theta tangent theta, what's secant the same thing as? 1 over cosine, right? So I can write that as 3 tangent theta over cosine theta. Multiply both sides by cosine theta. To get r cosine theta equals 3 tangent theta. And now we have this, hopefully, in a form where we can see how to rewrite some things. What can you replace r cosine theta with? X. And what can we replace tangent of theta with? Y over x, good. Y over x. And then if I rearrange, multiply both sides by x, we get 3y equals x squared. And notice again here we recognize that we have a parabola. That one was a little bit fancy, but it wasn't too bad, right? Just remembering what secant was in terms of cosine. In particular, I didn't want to play around with the tangent, since the tangent I knew how to replace. That was why I just played around with the secant. Questions on that one? Well, now that we've played around with some of these examples, let's go into trying to graph some things in polar. And we've already talked about a couple of these graphs anyway. I'm going to turn this heat. Pretty chilly. Yeah, it's too much. You can just bring it down too. You probably want to stay on anyway. Alright. So, I also want to, if you're doing some of these problems in WebAssign or wanting to practice more of these things as you go along, I want to give you some scrap. But I wanted to give you some extra polar graphs here that you can just practice with. This is for you to practice in case you want, if you're working on it when you're doing problems in WebAssign, or like I said, if you're just studying for the exam next week, that kind of thing. At least you'll have some extra graph paper here that you can use to practice. So let's chat a little bit about getting some graphs. We've already talked about a couple of these beginning ones even just a minute ago, but let's go through those before we get into some more complicated examples, as well as playing around with how to graph these things on your calculator, or if you're using Desmos online. All right, so we mentioned this just a minute ago, as a matter of fact, for r equals 4. So when theta is missing in your equation, that means theta can be absolutely anything you want. You can rotate it however you want, and it still satisfies the equation. Okay? What this equation, though, says is that r absolutely positively has to be 4, right? So again, what kind of shape will we get when we do that? Good, a circle, right? It's the circle right here that the r value is 4 all the way around. Okay. So that would be the graph of, well, pretend like that's a circle and not very, very wavy as I drew it around. But that would be our graph of r equals 4. Theta can be absolutely anything that you want, but as you rotate that theta around, that r value has to stay at 4 the whole time. Does that make sense? Same idea for the next one. Just kind of flip-flopped, right? The r value is missing, so r can be absolutely anything that you want, both positive or negative, but it says that the theta value has to be 3 pi over 4. Notice on our polar grid here, we've got all of these rays coming out from the pole, rays coming out from the origin. Those are all 15 degrees apart, or pi over 12 apart. In particular, you can see the pi over 6 and the pi over 3 is labeled. The one that's in between is pi over 4. So if we go to theta equals 3 pi over 4, that's this ray here. Right? So we'll get the line going through that ray. And then again, since r can be positive or negative, these values from the pole up and to the left would represent positive r values. But remember, when we have negative r values, you go kind of backward through the pole, that reflection through the pole. And so that's these ones that are going down to the right are your negative r values. Those make sense? Those aren't too bad, right? Those are the two different types of constants that you could have. These are the analogs in polar coordinates to horizontal and vertical lines. In particular, the first one, this one back up here, this is your analog of a horizontal line. I know it doesn't look very horizontal, but this is an analog of a horizontal line. If we think of r as being a function of theta in polar, or y being a function of x in Cartesian, this y equals a constant gives you a horizontal line that's still a function, isn't it? Right? Still a function of x. This is still a function of theta. It's a constant function. The second example is your analog of a vertical line. Again, doesn't look very vertical here, but if I want my r being a function of theta, this one theta has multiple r values associated with it. That's not a function anymore, right? Just like a vertical line is not a function, right? That one x value has multiple y's. So these particular examples are the analogs of horizontal and vertical lines in polar. Okay, let's do some more interesting examples, if you will. We're going to have a couple of plans of attack for plotting graphing polar coordinates. Graphing polar curves. One plan of attack is basically your main plan of attack that you learned when you were first first graphing equations back in algebra class. You pick some x's, got some y's, play connected outs, right? We're going to do the analog of that in polar. We're going to pick some thetas, get some r's, play connected outs. Plot the points, play connected outs. Okay? All right, so let's make a table. Let's pick some good theta values that we might know the function values for here. Let's say we use 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, pi. Let's start with that. Start there. I could have put some pi over 4s in the middle as well. Didn't feel like overkill right now. We will add more points in if we need to. But for right now, let's just start there. So basically what I've done here is just picked some thetas that are going to rotate from polar axis to the opposite of the polar axis, right? This goes from 0, pi over 2 to pi, right? Do you agree with that? All right, so let's just start plugging these in and see what we get. We put 0 in for theta. Cosine of 0 is 1. Good. So 1 times 3 just gives us 3. Put in pi over 6. Cosine of pi over 6 is 3 over 2. So I end up with 3 root 3 over 2. Oops. Cosine of pi over 3 is a half, so we end up with 3 halves. Cosine of pi over 2 is 0, so we end up with 0 here. And then we start going the other way, but negative. This will be negative 3 halves, negative root 3 over 2, and negative 3. End up with the opposites of the values that we got in the previous computations that we did. So let's just plot some points and see what happens. So remember again, The R value tells you how far out to go. The theta value tells you your rotation around, right? From that for positive x-axis, the polar axis. So right here would be your point 3, 0, right? Out 3 and don't rotate at all. Here's pi over 6, this line right here. We want to go out 3 root 3 over 2. Well, root 3 over 2 is about 0.86. I'll call it about 0.9 so I can do the multiplication a little bit easier. 0.9 times 3 is about 2.7. It'll be a little bit less than 2.7. Okay. So this circle right here is 3 units out, so we're a little bit less than that, so we should be about here-ish. Just again looking for the general idea. At pi over 3, which is this line right here, the R value is 3/2. Notice that each of these little grid lines in here are a half a unit apart, aren't they? Do you see that? If this is 2, halfway is 1. So this is a half, 1, 3/2, 2, 5/2, 3, 7/2, 4, and so on up the line. So on that pi over 3, again, which is right here, we want to go to 3/2, which is right here. And then finally, not finally, but this one here, the R value is 0. If the R value is 0, does the angle really matter? An R value of 0 says move 0 units from the origin. Okay? So we'll be right here. Now, the angle really does matter, which we'll talk about in a second when I draw it. But for the plotting the point purposes, the angle doesn't matter, correct? Right? If I'm 0 units from the origin, does it really matter what way I'm facing? I'm still 0 units from the origin. All right, what about the next one? Here's 2 pi over 3, this diagonal line here, right? Here's 2 pi over 3 here. Remember that when we think about doing these points, at least I typically think about doing the R and then rotating. If I were to go out positive, I would be up here in quadrant 2, wouldn't I? But this R value is negative. So instead of being up here in quadrant 2, where are we going to be instead? This is a negative R value. Instead of being up here, where are we going to be instead? In 4, we're going to be down here, right? Right? The negatives do a reflection through the pole. Okay. So this line right here is your 2 pi over 3 line. We're going to go backwards through the pole to 3/2. That's where the negative 3/2 comes from. Oops. Not 3 pi over 4. This should be 5 pi over 6. Gosh darn it. Sorry about that. When we do 5 pi over 6, that line is right here. But again, the value is negative. So instead of being in quadrant 2, we'll be down in quadrant 4, about a little bit less than 2.7 away from the origin. And then finally, when we get to pi, pi is over here. This is pi, isn't it? But again, we're going to go -3. So rather than going this way, we're going to go backward and land on that same point we were at before. Okay. So far, so good? Are we okay with how I got those points in there? That's the big thing to start with. All right. Well, now let's play connect the dots a little bit. We started here, went this way. Now this is where I said we're going to come to that angle is going to matter. Notice that this point at the pole came from 0, pi over 2. So when I draw this curve in, I want to make it try to be vertical here. Make that angle match the pi over 2. Does that make sense? I want to draw the curve. I want it to match the pi over 2 as we come in. Because the point is 0, pi over 2. Think of it this way. If you're standing at the origin, I want to face north as I'm looking, right? So if I have a point coming in, it's going to hit me like this. Or the curve coming in, it's going to hit me like this. Right? Rather than if I was facing this way, and then my angle 0, and my curve was coming in, I want it to come in this way. So when we draw this, it would come up and around and down, and then come out and around and up again. It's not the best picture I've ever drawn in my life, but what kind of a shape does that remind you of? A circle, right? So we end up with a circle there. Now notice we only went from 0 to pi, and we ended up matching back up again. If you go and pick some points between pi and 2 pi, rotating around this way, you'll end up landing on that circle again and just repeat the same circle over again. So again, this is a pretty rudimentary way of drawing a curve. This is like your Algebra 1 way of drawing a curve, right? Pick some values for the input, get some values for the output, pull up the points, connect the dots, right? So let's do the same thing for the next one. Let's pick some thetas, get some r's. Again, I'll start with some values for theta from 0 to pi. I'll add some more in there if I need to. Usually, if you do 0 to 2 pi, you're pretty safe. Because 0 to 2 pi will get you rotated all the way around one time, right? Just to save a little bit of time, sine of 0 is 0, so we'll get the 0 for the r. Sine of pi over 6 is a half, so we'll get 2. Sine of pi over 3 is root 3 over 2, so we'll get 2 root 3. Sine of pi over 2 is 1, so we'll end up with 4. And then they'll come back down again and get 2 root 3, 2, and 0 for the other ones. 0, 0 is right here. Again, if I want to try to draw this point, but if I want to draw my curve, I want my curve to be flat at 0, 0. All right? Because the angle was 0 at that point. So that's where the angle comes in. I want to be flat here. Pi over 6, 2 comma pi over 6 is here. 2 root 3. Again, root 3 is about 0.9. Double that, I get about 1.8. Should be a little bit smaller than that. So 1.8. Oh, sorry. Try that again. Root 3 over 2 is about 0.9. Root 3 is about 1.8. Sorry. 3.6 is where I'm looking. Pi over 3 about 3.6 is a little bit bigger than here. Pi over 2, 4 is here. And then start coming back around about here. And then right here. And then notice that 0 comma pi is back where we started. Pardon me. So again, if I play the connect the dot game, come around, Go here, come around, come back down. And again, notice that I want to make this flat when I'm at 0, 0 and 0 pi, right? Because I want that angle to make an angle of 0 on the left, or on the right hand side, and an angle of pi on the left hand side. Notice again here we get a circle, and if you check values between pi and 2 pi, it'll just retrace that circle again. So again, this is just a very, very rudimentary way to get some of the graphs. So we're going to try to talk a little bit more of an analytic way to get some of these graphs on Wednesday. So I'll do more of this on Wednesday. Have a good one. We'll see you then.